Question 7. A gas syringe containing 1 litre of air at 10 degrees Celsius expands as it is heated to 80 degrees Celsius. The pressure remains constant. Express the 1.0 litres in SI units. So litres are one of those intermediate units that are really easy to get caught out by. The link between these and our more standard measurements, I always think, is to remember that 1 litre is equal to 1,000 millilitres. So that's a lowercase l, millilitres. And 1 milliliter is equal to 1 centimetre cubed. So it's getting to the point where it's easier if you just remember probably what fraction of a metre cubed a litre is. But if we're really stuck, then we can remember this. So a litre is effectively a container that is 10 centimetres by 10 centimetres by 10 centimetres. Now, if you've ever had a litre carton of sort of something like orange juice, then it's not quite 10 by 10 by 10 centimetres, but you could see its volume is roughly the same as something that's 10 by 10 by 10. So that's kind of how I have in my head what 1 litre is. So in my head, 1 litre is 10 cubed centimetres cubed, which of course is 1,000 centimetres cubed. Also in my head is what 1 metre cubed is in terms of centimetres. You've probably watched this at least once in one of the other videos, but 1 metre by 1 metre by 1 metre is 100 centimetres by 100 centimetres by 100 centimetres. So 1 metre cubed is 1 million centimetres cubed. So I've got 1,000 centimetres cubed in a litre. A metre is 1 million centimetres cubed. So if you didn't remember, 1 litre is 1 times 10 to the minus 3 metres cubed. So a slightly tortuous way of getting to it, but if you're ever stuck, I think as long as you remember this line here, then you can get to that from sort of basic principles. B, explain using the particle model how the pressure can remain constant in this example. So this is, a relatively complicated idea. I'm going to draw a little diagram to help us in this case. So initially, my cylinder's at a low temperature and is relatively small. And then we heat it up, same cylinder, and it expands outwards slightly. So the plunger's expanded outwards at a high temperature. And so what we want to do is to show that the pressure remains constant. Now, pressure we know is caused by two things. There's how hard the particles hit the side and how frequently they hit the side. So the particles are traveling faster. So they hit the sides harder than they were before. So that alone would make you think the pressure should increase, but the pressure has remained constant. So in addition to them hitting the sides harder, they must also hit the sides less often. And therefore we can kind of say the syringe must expand to lower the rate of collisions. So despite the fact that they're traveling faster, because it's got bigger, they end up hitting the sides less often. Now, this is quite a difficult diagram to draw then. I suppose the bit that we could concentrate on is the fact that the horizontal dimensions are the only ones that matter. It hasn't expanded in the vertical direction. So if I draw in two particles, I'm going to make sure that in my first one, they hit the sides quite often by having one that does this and one that does something like this. There we are. So in my picture, in my first picture, it's just coming off there, let's say, we've got this one hitting the sides 1, 2, 3 times, this one hitting twice. So we might just note down that we've got a total of 5 collisions between particles and walls in my first box. Now, when it comes to my second box, if I put my particles in the same place, I'm going to make the arrows longer, but the distance this has to travel before it hits the wall is already longer. So this one, even though it's traveling much further than the first one, only makes 1 collision with the wall. The second one probably less affected, so it's still going to make 3 collisions with the wall in a relatively short space of time. This arrow should be longer, so maybe I should have extended it, shouldn't I, before I finished drawing it, but we don't want it to come into contact with the wall at the top. Cheating slightly to make sure we get the answer that we want. So in this one, there's a total of 4 collisions. So in my first box, we've got more soft collisions, and in my second box, we've got less hard collisions, and that's how we can say the pressure can remain constant in this case. C, calculate the new volume of the gas syringe. So here we can use the combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. Things that are changing. So we had an initial volume V1 was 1 litre. V2 is what we're trying to find. P1 is equal to P2. We haven't been told the value. Again, I'm going to go and edit the question here and say that they're both at atmospheric pressure. So this is going to be 1.0 times 10 to the 5. But in this question, it doesn't matter because they're going to be the same. And T1 is written as 10 degrees Celsius, but we're going to put it in as 283 Kelvin. T2, it's heated to 80 degrees Celsius, so that is 353 Kelvin. Running out of space, I'm just going to come up here to the side. So I want to find V2. V2 is equal to V1 T2 over T1. So that's 1.0 times 353 divided by 283. So that's 1.24. So we're going to put 1.2 litres. And if we've done it in meters cubed, of course, that means it's 1.2 times 10 to the minus 3 meters cubed. For D, says calculate the number of air particles present in the syringe. So we need a pressure. So I'm going to go back and edit this question up here at the top. It remains constant at 1.0 times 10 to the 5 pascals. So that's atmospheric pressure. So to calculate the number of air particles present in the syringe, I'm going to use PV is equal to NKT. I can pick either the initial or the final state. It doesn't matter too much which one I pick, but seeing as V2 was a calculated value, it's probably better to use the original values. So the original pressure was 1.0 times 10 to the 5 pascals. The original volume was 1.0 times 10 to the minus 3 meters cubed. This is going to have to be in meters cubed if we want to get the right units. And the initial temperature was 283 Kelvin. So I'm going to rearrange this. Number of particles is equal to PV over KT. So that's 1.0 times 10 to the 5 multiplied by 1 times 10 to the minus 3 divided by K. His value's gone out of my head. It's at the top of the page, isn't it? 1.38 times 10 to the minus 23. There we are. One point three eight times 10 to the minus 23 multiplied by the temperature is 283. Times 10 to the minus 23 multiplied by 283. So 2.25, 2.6, sorry, 2.6 times 10 to the power of 22 particles.